Hello and welcome to this video walkthrough on simulating the Heston model in Python. In this video, we will be exploring how to model stochastic volatility and its effect on asset prices using the Heston model. We will define the model parameters, perform Monte Carlo simulations, and plot the resulting asset prices and variance over time. Additionally, we will show you how to capture the volatility smile in option pricing using the Heston model. So, let's get started. Welcome back. In this cell, we have a simple markdown title that tells us what we will be doing in this notebook, simulating the Heston model in Python. This is the first step in our journey towards modeling stochastic volatility and its effect on asset prices using the Heston model. In the next cell, we will dive into the details of the Heston model and why it is a useful tool for simulating stochastic volatility. We will also discuss its advantages over the Black-Scholes formula. So, let's move on to the next cell and learn more about the Heston model. Welcome back. In this cell, we have some comments that explain why the Heston model is a useful tool for simulating stochastic volatility and its effect on the potential paths an asset can take over the life of an option. The Heston model is popular because it has an easy closed-form solution for European option pricing, no risk of negative variances, and incorporates the leverage effect. This allows for more effective modeling than the Black-Scholes formula, which assumes constant volatility. In the next cell, we will import some necessary libraries and begin diving into the details of the Heston model and its advantages over the Black-Scholes formula. So, let's move on to the next cell and continue our journey towards modeling stochastic volatility using the Heston model. Welcome back. In this cell, we have some Python code that imports necessary libraries for our simulation. We import NumPy, Seaborn, and matplotlib.pyplot for data manipulation and visualization. We also import a library called py_volab_vectorized, which has a function for calculating implied volatility. In the next cell, we will define the parameters for our simulation, including the asset price, time, risk-free rate, and number of time steps in simulations. We will also define the Heston model parameters, which include the rate of mean reversion of variance, long-term mean of variance, initial variance, correlation between returns and variances, and volatility of volatility. So, let's move on to the next cell and start defining our simulation parameters. In this cell, we define the parameters for our simulation. These parameters include the asset price, time in years, risk-free rate, number of time steps in the simulation, and number of simulations. We also define the Heston model parameters, which include the rate of mean reversion of variance, long-term mean of variance, initial variance, correlation between returns and variances, and volatility of volatility. Finally, we output the values of theta and v0. In this cell, we define a function called Heston_model_sim that performs a Monte Carlo simulation. The function takes in several parameters, including the initial asset price, initial variance, correlation between asset returns and variance, rate of mean reversion in the variance process, long-term mean of the variance process, volatility of the variance process, time of simulation, number of time steps, and number of simulations. The function then initializes other necessary parameters and creates arrays for storing prices and variances. It samples correlated Brownian motions under the risk-neutral measure and calculates the asset prices and variances over time using the Heston model. Finally, it returns the resulting asset prices and variances as NumPy arrays. We will use this function in the next cell to perform simulations with different correlation values. In this cell, we are using the Heston_model_sim function to perform Monte Carlo simulations with two different correlation values, ρ_p and ρ_n. We pass in the initial asset price, initial variance, rate of mean reversion in the variance process, long-term mean of the variance process, volatility of the variance process, time of simulation, number of time steps, and number of simulations as parameters to the function. The resulting asset prices and variances are stored in the S_P, V_P, S_N, and V_N variables. We will use these variables in the next cell to plot the asset prices and variance over time. In this cell, we are plotting the asset prices and variance over time using the Heston model. We start by creating a figure and defining the size of the plot. Then, we use the NumPy library to create a linear space for time. We plot the variance over time using the V_P variable. Finally, we set the title, x-axis label, and y-axis label for the plot. We then use the plt.show function to display the plot. This plot helps us visualize the variance process over time. In the next cell, we will plot the asset prices over time. In this cell, we are plotting the asset prices over time using the Heston model. We start by creating a figure and defining the size of the plot. Then, we use the NumPy library to create a linear space for time. We plot the asset prices over time using the S_P variable. Finally, we set the title, x-axis label, and y-axis label for the plot. We then use the plt.show function to display the plot. This plot helps us visualize how the asset prices change over time in the Heston model. In the next cell, we will plot the asset price distribution with different correlations. In this cell, we are plotting the asset price distribution with different correlations using the Heston model. We start by simulating a geometric Brownian motion process at time t using the S0, R, theta, and t variables. We then create a figure and define the size of the plot. We use the Seaborn library to create kernel density plots for the asset prices with different correlation values. We also plot the asset prices using the GBM variable. Finally, we set the title, x-axis label, and y-axis label for the plot and display it using the plt.show function. This plot helps us visualize the distribution of asset prices under the Heston model with different correlation values. In the next cell, we will capture the volatility smile in option pricing. In this cell, we are capturing the volatility smile in option pricing using the Heston model. We start by setting the correlation value to -0.5 and using the Heston_model_sim function to simulate asset prices and variances. We then define a range of strikes and calculate the option prices for both calls and puts using the mean of the maximum of the difference between the strike and asset price and 0. We calculate the implied volatility for both calls and puts using the implied_volume function. We then plot the implied volatility against the strike using the plt.plot function and set the title, x-axis label, and y-axis label for the plot. This plot helps us visualize the implied volatility smile from the Heston model. And that concludes our walkthrough on modeling stochastic volatility using the Heston model. We have explored the effects of different correlation values on asset prices and variances, plotted the asset prices and variance over time, and captured the volatility smile in option pricing. We hope this has been informative and helpful in understanding the Heston model and its applications in finance. Thank you for watching.